very important topic. Gravitational instability. Instability, the good or bad? What do you think? Good? Instability, the good or bad? If you go to your psychologist and you say I'm stable, or your doctor, it's good or bad?
If you're an artist, then it's good.
For the psychologist, it's good. Otherwise, you will not make money, huh? Also, if we didn't have gravitational stability, we were not here.
Yeah.
Okay, so that's the driver for everything. That's what the standard model of cosmology is telling us. Okay, that actually everything, in terms of the formation of structure, formation of everything, formation of life, us, all of us, you know, it's being driven by gravitational instability. So before going to do gravitational instability in the cosmological context, I want to do it in kind of a more general context. Now, I think that you all sort of agreed with me that when we did the top hat model, that it was clear, especially for the Einstein universe, that if we had like one sphere over which the density, the over density was positive, let's say we started at the theta, that this sphere was unstable. Then what do we mean by unstable? I mean, you start with a small perturbation, and then the perturbation, the amplitude of the perturbation grows. Okay, it doesn't decay. Okay, that's the meaning of instability. Now, I want to start with something kind of more general, in the sense it's more physics and less cosmology or astrophysics. And what I'm referring to is the Jeans instability. I guess that all of you at least are familiar with the notion, with the name Jeans instability. You say no, wait. You say no, or you say yes. So you have encountered before the Jeans instability? Fine, that's okay. That's the reason why you are here. Okay. Then I'm double happy that actually that we managed to squeeze it into the schedule of the school. Okay, the Jeans instability. Forget about cosmology. Okay. What?
Oh. No, forget. We are in cosmology.
Forget about cosmology for a second. Okay. And assume that you have some, you know, we have a uniform medium, you know, I'm talking now from the point of view of fluid dynamics, okay? So we have some stable configuration where we have, on the one hand, we have some density field, and we have pressure gradient, okay? And gravity balances the effect of gravity. You know, that's how we are getting the stability of stars actually is made by the fact that actually pressure is balancing the force of gravity. Okay. Let's take even something simpler, okay? Let's say that we can define in Newtonian dynamics a uniform medium, okay, with some density, okay, and some pressure. But now, because it's uniform, then everything is uniform, and so the density is constant and the pressure is constant. The pressure is something like, let's say that it's 1 or P naught. Okay. Anyway, do you think that Newtonian dynamics allows for this kind of configuration for a homogeneous infinite background of constant density and that's a constant pressure? Do you think it's possible from Newtonian dynamics point of view, not a GR point of view? Can it be something that, like this zeroth order configuration that I'm presenting here? Is it possible by Newtonian dynamics? We are voting. Who thinks that it's okay with Newtonian dynamics? Is it okay with Newtonian dynamics? You say that yes. Who said that it's not? Okay. 1 and 1, and the rest are waiting to see for the outcome. All right. Okay. If it's so I'm going to treat it by Newtonian dynamics. Okay. So if it's infinite, homogeneous, then it means that actually there is no preferred direction. Okay. I cannot have a gravitational field. I mean, gravitational force or acceleration. You know, it should be zero because gravitational field is a vector. So if it's non-zero at any point, it has a direction. If it has a direction, it breaks down the assumption of the homogeneity and isotropy. All right. So from this point of view, I should expect that actually G at any point should be zero, and because of that, also the gravitation. I mean the pressure. So the pressure gradient should be also zero. Okay. At the same time, you know, I'm using Gauss theorem, okay, the thing that we're using all the time when we're doing electromagnetism, first year of the university. Actually, I can cut a sphere. Let's say that, you know, this is I'm cutting, you know, that's just now I'm looking at it from above, let's say. So I have a sphere, I'm cutting a sphere, okay, and I'm just picking up the center of the sphere triangle because any point is as good as any other point, right? Now by Gauss theorem, actually I can, because then I have spherical symmetry about that point, then I can use Gauss theorem, and then I find that actually the gravitational field should be radial inside at any given point. Alright, so I'm getting a contradiction. Right? If I choose my sphere to be, let's say here, then the forces will be directed toward that point. So I mean, Newtonian dynamics cannot actually handle such kind of a configuration. When it comes to infinite medium, actually it breaks down. Something in the formula cannot handle it. Okay? So the whole idea that you can write and assume that you have something like that, actually, in the literature sometimes, it's called James swindle. You know what swindle is? It's like cheating. So you're cheating when you're saying that you have something like that. All right, so we are going to stay with the cheat. Okay? And we are going to suppose that, okay, you know, we cannot, but let's do something local, and everything that we do local is okay in Newtonian dynamics. All right, so let's now look at this kind of configuration and say that we take a sphere, okay, and we squeeze it a little bit. Okay, when we squeeze it a little bit, so this is the sphere that we have. So we have here like a sphere where we are doing our perturbation, and we increase the density. So the original density was 1 and I increased the density a little bit. Okay, what happens when I increase the density? How the gravitational field changes? It increases. Okay, so all of a sudden I have here a net gravitational force, which is radial. It points to, let's say if everything is kind of spherical symmetric, I have a radial force that actually wants to make this sphere to start to collapse. Okay, but at the same time, because I'm talking about a hydrodynamical system, and I have here pressure. What happens when you increase the density? What happens to the pressure? It increases, right? Let's say that we are dealing with adiabatic changes. So we do changes slow, we don't have viscosity, we don't have heat conduction, all the things that are changing the entropy. And so P, so the entropy is constant, also after the perturbation, so that we have P is the pressure, the equation of state that we have is that P is the function of rho only. Okay? And so whatever is the entropy, so that will be the relation. And so when we are changing so before doing any kind of calculation, so what happens when I'm squeezing the sphere? What happens to the pressure? It increases, okay? So now I have delta rho, so I have gravitational force on the one hand, but I have also I'm increasing the pressure. So the pressure inside is larger than the pressure outside. All right? Let's say, so if this is positive, this is positive. So this is positive. So now, so what happens when I have excess of pressure? Well, the pressure gradient actually goes from the outside inside. So what happens? We have actually the pressure wants to act in the opposite direction. So gravity pulls inside, and pressure pushes outside. Okay. So I have now two forces. On the one hand, I have a delta G that is, let's call it kind of inside like that. Okay, that would be like inside. And the pressure, delta P, gives us the pressure gradient, okay, gives us actually force that acts outside. So now we have a competition. Okay, gravity wants, to take everything inside. Pressure wants to push everything outside. Who is going to win? Okay, of course it depends, but we want to see how it depends. Okay, so we can say that actually, before doing any kind of calculation, I want to show you how we can estimate what it depends on. Okay, so let me write it. If I'm making the change of the density, so delta P equals to dP by d rho. Now that's a dP by d rho with fixed entropy, it's an adiabatic chain, okay, times delta rho. Okay, so any change in delta rho gives me a change in the pressure. Okay, do you know what this quantity is? dP by d rho at a constant entropy. That's the sound speed squared. Okay, so essentially, sound waves are actually pressure waves. Okay, when you make a small perturbation in the density, you have a small perturbation in the pressure. Okay, and so the speed of sound squared is defined as dP by d rho at a constant entropy. Okay. Now, actually, the speed of sound actually is the thing. If I'm making any kind of perturbation for the pressure, for example, my vocal cord when I'm speaking, I'm making small perturbation to the pressure. Okay, this small perturbation is moving within the air. That's the medium that we are talking about, and it reaches your ear. Okay, at what speed? At the speed of sound. So actually, the speed of sound is the speed at which small perturbations in the pressure actually can propagate in a hydrodynamical medium. Okay. So we have from the pressure point of view, we have this kind of a typical velocity. All right. Now, if I'm making any change in the density, it implies, suppose that I didn't have any pressure to counterbalance the gravity, okay? Then we know that actually the free fall collapse time goes like, so the gravitational time, okay, actually goes like 1 over square root of G of 4, right? And if you have a gravitational medium, if you have like the sun, okay, the sun is in hydrostatic equilibrium, all right? Sure, right? And I, stupidly enough, I go to the sun and I hit it very strong with my knee at one side of the sun, okay? So I'm perturbing actually the hydrostatic equilibrium of the sun. Part of this thing, actually, I'm changing the density at some point. How the sun is going to react to it in terms of the gravitational field. The typical time over which things are going to change due to the gravitational field are always, or the time scale is always like 1 over square root of G1. Okay? So if you wish that, and that's the unperturbed density. Okay, that we get there. So we have a typical time, and we have a typical speed. Alright? So I have a velocity, I have time. Okay, so that's the gravitational time. Okay, so the product of these two things what gives me a length scale, right? It gives me a length scale, okay? So we're going to define it, so we'll do a calculation. But let's call this critical length scale. I already call it. That's the lambda genes. Okay, that's the critical density. That's the dependence that we just said before. Okay. So now let's see what happens. Suppose that I make the perturbation on a wavelength. So I'm just, introducing some kind of a sine wave, okay, with a wavelength that is much, much larger than the Jeans wavelength, okay. So I'm making the perturbation, the time scale for the gravity to act is tau grav, okay, that I derived here. Now, in order for the pressure to balance the change that I put in the gravity due to the gravity, all of its the effect of the pressure will propagate with the sound speed. So the effect of the pressure actually can be at most the typical length, the typical wavelength over which the pressure can affect the gravity is the speed of sound times tau grav. So when I'm introducing a perturbation where the wavelength or the typical length scale of the perturbation is much larger than the Jeans length, then the pressure simply doesn't have enough time to balance it. Because by the time that the pressure will do something, and it will be on a length scale much smaller than actually what I put in, gravity is going to finish whatever it wants to do. So if I have this kind of thing, then gravity wins. Okay. On the other hand, if I have the typical length scale is much smaller than the Jeans, let's call it just with the J here. Okay. Then we can make a small perturbation in the density, and pressure has enough time actually to go and to erase this kind of thing. Okay, so it's the pressure that wins. Okay, so that's the nature of gravitational stability. So if we have something to balance the effect of gravity, like something that we did take into account when we started with the Topic model, then we have to find out what the Jeans critical wavelength or length scale in order to see if we can ignore pressure or not. So we have to calculate, we have to know what the pressure is. We have to know what the equation of state is. Namely, we have to calculate and find out what's the sound of speed. And if we know that, we can say, is it okay for me to ignore the pressure? If it's okay, I can proceed with whatever we did so far. If not, then we have to take into account the effect of pressure. All right, so is it clear? All right, let's do it now systematically. How many of you took a course in fluid mechanics? Only two? The rest of you didn't take a course in fluid mechanics? All right. It's not all right, but that's what we have. Okay, so I'm going to write and I'm going to start with, so now the description of our system is a hydrodynamical description. And what's hydrodynamical? I mean, we describe the mass in terms of the density. So we have a density field. So it's, let's say, it's a density, it's a field, but it's changing as a function of time. We talk about the velocity. So now it's the velocity of an element of mass, at what velocity it moves. We talk about pressure. And I think that's all that we need here. All right, if we ignore effect of viscosity, if we ignore effect of heat conduction, then actually we have two equations that are that govern the evolution of such a system. Okay, so the first equation is the equation of the continuity equation. And the continuity equation is telling us that the partial time derivative of the density plus the divergence of rho times v equals to 0. And that's assuming that, you've seen it before, I'm sure. It's assuming that we don't have, we have mass conservation, we don't have any chemical reaction or whatever that, mass changes its form or something escape via radiation by decay of particles or something like that. It's down to earth, simple hydrodynamics. And so that's actually that equation just expresses the mass conservation. And the other equation, it's called the Euler equation, is partial derivative of v plus v dot grad times v equal to minus 1 over rho, the gradient of the pressure, minus the gradient of the gravitational field. So we're assuming that we have gravity. So actually it's like, this is the basic question that needs to be solved when you're dealing with like stellar structure. Okay? Now in stellar structure, like stars of the main sequence are in equilibrium, so nothing is moving. So if you assume that the velocity is 0, then actually the whole right hand side of the equation is 0. And then you have that actually that the pressure, the gradient, the force of gravity, so that's gravity that we have here. Gravity. And here what's written is nothing more than the gravitational field, the G. Okay, so the gravitational field is being balanced by the pressure gradient. Okay, that's what we have here. All right? And so what we have here, this is acceleration. Acceleration. okay, and that's like force. So it's like the second law of Newton, F equals ma. All right. So let's assume, and that's actually the genes involved. We are making the assumption that we have a system for which rho equal to rho naught, which is some constant, v equals to 0, and p equals to some p naught, which is constant. Okay? And then we have equation of state where Cf squared equal to dp by d rho is constant entropy. All right, so you have this system. This system can live happily from now to eternity if we forget about the fact that such a system cannot exist at all. All right, and then we say, all right, let's make small perturbation. All right, so we say, okay, rho is now, we call it rho naught plus some rho 1. V is just this V1 because we don't have any. The hydrostatic equilibrium actually doesn't allow for any velocity, and we are making a small perturbation for the pressure. So P equals to P naught plus P1, and we have the relation that P1 actually equal to some speed squared times rho 1. So let's put it in the equation. Linearize, so we have, these are the two equations, continuity, all the equations, they are the exact equations. So what I'm going to do is to substitute here that rho is like whatever I wrote here, and I'm going to linearize the equation, right? If you want to do a stability analysis, that physicists know to do two things: to solve spherical curves or atoms or stars or whatever, and to do stability analysis first of all by linearization. That's what we are trained to do, and that's what some of us are being paid later on to do for the life. Okay, so let's do it. So after linearization, what we get? One more thing that we need to write. I can write it here. Is that the gravitational potential, right, here it's written in terms of the gravitational potential, is related to rho 1 by the Laplace equation. So Laplacian of phi 1 equals to 4 pi g rho 1. All right, we have everything. It's just a matter of playing a little bit with the mathematics. And the linearization is giving us the following. So we have d rho 1 by dt plus rho naught divergence of v1 equals to 0. So that's the first equation. Second equation is, you see this this part actually doesn't appear because it's a second order in the velocity. So what we have here is d by dt of v1 equals to minus cf squared divided by rho naught, okay, times Laplacian times the divergence of rho 1 minus the divergence of phi 1, like that. Okay. please pay attention that he was here with the row naught and not the row with the perturbation, with the addition of row 1, because I'm linearizing. The only leading term that I have is actually in the gradient of row 1. Okay, and on top of it, we have a third equation, Laplacian of phi 1 equals 4 pi g over 1. Okay, so what I'm going to do is actually, I'm going to take the time derivative or the partial time derivative of equation 1, and I'm going to take the divergence of equation 2. All right, and when I'm doing these two things, let's see. So actually, the reason that I want to do it is that I want to get rid of the velocity. All right. You see, when I'm taking the second derivative, the derivative, the time derivative of the first equation, I have here d by dt of, I have the second order derivative of rho 1, and I have here the divergence of, the time derivative of the divergence of the velocity. When I'm taking the divergence of the second equation, what I end up with is actually time derivative of the divergence of the time derivative of v1. So the two of them actually cancel, and what I end up with is the following. So what I'm doing, I'm getting d squared by dt squared of rho 1 minus cs sound speed squared times the Laplacian of rho 1 equal, okay, now because I have here the divergence of alpha on the graph, I'm getting the Laplacian equal to 4 pi g rho 1. So rho naught, rho 1. Okay, so that's the final equation that I'm getting. Note that this is a second order equation for the density perturbation, and I can start to solve it. The way to solve it is actually by expressing it in terms of the Fourier transform. So what I'm getting, I'm saying that let's expand rho 1 of x and t as the sum of plane waves. Okay, so it's the sum of k and omega. But that's why it is kind of a sum, as you can write it, right? So I have this amplitude or coefficient, which is the function of k and omega. Exponent of, what do we have? Minus I kx minus omega t. All right? So now when I'm substituting this representation of rho 1 into the equation, note that actually what I have here, each one of these derivatives that I have here is going to give me either like k or omega. So what I'm going to end up with is a dispersive relation between omega and k. Okay? So when I substitute it into this equation, it's a linear equation. So I can do it term by term, right? This is the sum, and I can do this equation term by term. So what I'm getting is that by doing this kind of presentation, actually I'm turning the differential equation that I have here into a algebraic equation. Okay, that's why we are using this sum of plane waves. And so we get here omega squared equal to cs squared times k squared minus 4 pi g rho naught. Note that the whole dimension, the dimensionality of this equation is 1 over time squared. Right? Omega is 1 over time, so 1 over time squared. What I have here is the velocity. Okay, so again, it's 1, and so velocity is like distance divided by time. So square, and k is 1 over distance. So everything here has the dimensionality of 1 over time squared. Okay, so I mean, in order to see if a certain mode is stable or unstable, so first of all, like when I'm writing this kind of a general expression, at first k and omega are just arbitrary, okay? But then I know that in order to obey the equation, in order to be a solution of the equation, actually, once I fix k, let's say, omega is not arbitrary. Omega is a function of k. That's the nature of the dispersion relation that we have here. So we get here omega squared, and so the condition for stability or instability is that when omega squared is positive, we have stability. And whenever omega squared is negative, we are getting instability. Is it okay? Are you with me about it? Is it clear why we have this condition? Speak. Is it clear or not? All right. Okay. One great guy here. I think that after almost a week that we were spending together, if you don't speak, I don't know how much you know or you don't know, okay? The idea is to make you understand and to know, okay? So if you're saying shy, you will not know. You will not learn, okay? So omega squared, all right, if it's positive, then the square root of omega squared is just a real number, all right? So if it's a real number, then actually rho 1 of x and t is just a sum, a superposition of plane waves, right? What's written here is a plane wave, okay? And if omega is a real number, positive or negative, it doesn't matter. What we have is that things are just oscillating. The perturbation, the amplitude of the perturbation doesn't grow in time, okay? It stays, you know, the initial amplitude that we put in by hand, or like the way that we generate or prepare the perturbation, doesn't change in time. That's the meaning of stability. All right? On the other hand, if omega squared is negative, it means that the square of a negative number is a complex number. All right? So if it's a complex number, it can be either I, some positive real number, or a negative real number, okay? We have two options, okay? So now if this is actually a complex number, I times the complex number becomes a real number, okay? And with a real number, then we have like two modes, because we have two solutions for omega squared, right? So what we are going to get actually is that because we have a minus I here, and we'll have another I coming from here, so it doesn't matter which one, the positive or the negative. So one of the solutions actually is going to explode, as we say. It's going to grow exponentially. So we start with a smaller perturbation, and after a very, very short time, actually it's going to increase exponentially. As long as it were in the linear regime, this is the good description, and then the amplitude of the perturbation is going to increase. Okay, so the limit of stability, or the critical, we're going to find the critical wave number, or wave number, or wavelength, actually that distinguish between being stable or being unstable. Okay, so let's do it. Okay, so the gene scale now is defined to be the one for which omega squared is 0. So we say that the gene scale is defined in terms of wave number is where CS kj squared equal to 4 pi g rho naught. Okay? So what we find, if we are now writing it explicitly, we find that the critical gene's wave number, sorry, kj, equals to 4 pi g rho naught divided by c squared square root. If I write it in terms of wavelength, not number, and then kj is 2 pi over lambda j. Okay, the lambda j equals to pi over g rho naught squared times cs. I erased it, but when I did this simple sort of dimensionality analysis, actually what I found that the lambda j I said is roughly cs times 1 over square root of g rho naught. Okay, so I was wrong just by a factor of square root of pi. Nothing. All right. So this actually gives us, in a very precise and exact way, actually, what's the definition, the mathematical definition of the critical Jeans length or Jeans wave number of that metal, and we have it from here. So essentially, its lambda Jeans is roughly, gravitational time, which is roughly 1 over square root of g rho naught times the sound speed. And remember, it always goes like that. As you go to larger and larger linear scale, okay, gravity wins. Gravity wins on large scales, pressure wins on small scales. Okay, gravity is a long-range force, and if you put your perturbation on large enough scales, then gravity wins. By the way, the reason that gravity wins here is that within the gravitational instability, within the Newtonian dynamics, then gravity propagates with infinite speed. Okay? But in hydrodynamics, pressure propagates with a finite speed. But that's okay, because we know that gravity, okay, if we are doing a GR treatment, it doesn't propagate, instantaneously with an infinite velocity. It propagates with the speed of, with the velocity, with the speed of light. Okay, we see. Now, for all kind of non-relativistic cases, we always have the case that c is larger than the sound speed. Okay, but there are some cases when we are talking about cases where the fluid that we have is a radiation fluid. It's a radiation-dominated fluid, which is like what happens for very massive stars, and they are becoming their pressure becomes radiation-dominated, or in the early universe, where the universe is radiation-dominated. In these cases, the speed of light and the sound speed are almost the same. Okay, so one cannot predict. Both of them have to be taken into account. All right. So that's much to describe the instability of a system that doesn't exist in reality. Okay, but we get the idea. Even if it really doesn't correspond to any being system, we get the idea of what's the meaning of the gene scale, what's the meaning of what we're doing here. And the gene analysis is still relevant. For example, if you consider, for example, like stars in hydrostatic equilibrium, and one can perturb the hydrostatic equilibrium, Now, it's not going to be there, I mean, you cannot use like plane waves and stuff like that, but the basic idea and the basic scale of instability remains the same. I mean, the calculation is much more complicated because we are not perturbing a homogeneous background, but something with gradient and some structure and so on, but the idea is just the same. So the Jeans analysis is important, even if we solve here a very kind of idealistic system that doesn't exist in reality. All right, now, we're done? Yeah, we're done. Okay. Wow. It took more time. All right. Okay.
I have a question.
Yeah, I'm listening to you.
So, also, we are solving the hydrodynamic equations, assuming that this fluid is confined to a portion of the universe that is not expanding. So, is it possible that, I mean, is there a case where the expansion of the universe?
No, the way, no, it's very, doing in GR. In GR, you don't have any problem with infinity or anything like that. The way to do it properly is in GR. It can be done. It's been done. Okay? But in order to just to show the analysis, and now we are not doing any GR thing here. Okay? But I mean, like, yeah, I mean, if you want to do the instability and so on, you have to do it by in the proper GR. I mean, going to do a large scale, you go GR. All right. So we have to finish, and maybe for one time I'm finishing before the time, just because I have too much to do after the time. And so let me say, because I don't want you to get used to the fact that I can finish ahead of the time. What I'm going to do in the afternoon is to do the same analysis, but the background is going to be the Friedman solution. So we are going to perturb the Friedman solution. So we are going to work with quantities that already, so the zeroth order solution is the universe that is expanding. So the background is still uniform spatially, okay, in terms of the, x, y, z, but it's changing in time. So the difference between what we did here and what I'm going to do after is to work against a background that is changing as a function of time. All right? And we are going to work it out. Let me say one thing here. I mean, when we have that omega, I mean, if omega is divided as, let's say, like I alpha, okay, then the plane wave that we have here, the time evolution is going to be like A, some K omega. I mean, omega in I alpha corresponds to the case where omega squared is negative, okay, where K is smaller than K genes, okay, so we have something like that. And then we have, it's okay, we have one minus I k x, that's okay. But then we have, like here, what do we have? We have minus and minus is a plus, but then I times I is minus. Okay, let me put it like this. Let's say that we have plus minus I alpha because we have to take the square root of this quantity. Okay, then we have actually plus or minus alpha t. All right, we have two solutions. Actually, so when the instability is occurring against a static background, a background that doesn't change in time, what we get here is exponential growth. And you know, exponential growth are growing very, very fast. Okay? And so the system is very unstable. When we do it in cosmology, we're doing it against a background that is sort of, you know, the density is decreasing in time all the time, just because of the expansion of the universe. And then we see that the major difference between the solution that we got from this classical Jeans analysis to what we get in cosmology is that the time growth of the instability is algebraic. It goes like some power law of time. While here it goes like exponential in time. So it's a much much slower instability when we are doing it in an expanding universe. Okay, go to it.
So I have